Hypothetical syllogism. All right, good. So now you've learned those 9. Let's learn 10 more. Because 9 isn't enough. And you'll notice you will have already seen them because the part just inside the front cover of your textbook where they got the 9 inference forms, they've got the 10 equivalence rules. All right. Why not just list 19 rules? Why separate them into groups? Answer, because they are different. That is a good reason for separating them. What are the important differences? Well, one important thing about the inference forms, the 9 that you have already learned, is you can only apply them to entire lines at a time. And what I mean by that is, suppose you had something like this. If P and Q, then R. Well, you have a conjunction here. Can you simplify it? What's the answer? The answer is no, you cannot. Why can't you? What's that?
You would need another premise.
No, simplification is a one premise one, remember? So, well, in contrast, suppose you just had this. Or, no, let's put it this way. Could you simplify this? Yes, you could. So why can you simplify this when you can't simplify this?
Doesn't work on conditional.
Yes. In other words, you've got to look at the main connective. Simplification only works on conjunctions. This is not a conjunction. Even though there's a conjunction in it, it's not the main connective. So the whole thing isn't a conjunction. The whole thing is a conditional, because that's the main connective. Whereas here, the whole thing is a conjunction, so you can simplify. And you could either get P, or you could get if Q then R. Either, either of the conjuncts. Okay. So, similarly, if you had, suppose this is premise 1 and this is premise 2, can you do modus ponens if you have this and this? Can you do modus ponens? Yes or no? Yes, you can, because this is a conditional and you've got its antecedent, so you would end up with R. But suppose instead of this being number 1, this is number 1. Can you do modus ponens now? No, because this isn't a conditional. So you can't do modus ponens there. So you can only, what is the main connective on the entire line really matters for the inference forms. Not so the rules of equivalence. The rules of equivalence are a lot more flexible, you might say. Let's look at the most mind-numbingly obvious rule of equivalence, and that is double negation. So, today is Wednesday is logically equivalent to what? Today is not Wednesday. Yes, because obviously there are only 2 truth values, and if you start with true, you negate it once, it becomes false. You negate it once, it's back to true again. So double negation takes you away and brings you back to the original truth value, which is why they're going to be equivalent. Now sometimes we forget this when we say things like, I ain't never going to do that again. But that's just the way we talk. That's colloquialism. But in logic, double negation is the same as the original. All right. Let's illustrate a fact about double negation. So, and by the way, in the book, notice that one obvious way in which the rules are different. Here, the rules are little arguments, premise, premise, conclusion, or in the case of these ones, there's only one premise. But it's still a premise and a conclusion. Whereas here, they're written out as either, they're written as either side of a if and only if, which actually here is being, in most of these, the if and only if symbol is just being used as a logically equivalent sign. So it's saying, you're saying this is logically equivalent to this. The only time it's actually used as a biconditional is in the rule called biconditional. And that's when it's being used on one side of it. Whereas all the rest of it, this symbol just means the thing on the left is logically equivalent to the thing on the right. But perhaps an easier way to write this is the way that it will occur on an actual line of a proof. And that might be, suppose you had P on line 1, and you did double negation to it, you would end up with not P. Okay? That would be applying double negation in practice. Double negation, by the way, I call essentially a tidy up rule. If you're doing a proof, and you think, yes, double negation, that's the key to this proof, you're doing it wrong. Double negation is never the key to anything, okay? It's just a tidy up rule. If you think it's the key, probably you're doing single negation, and that's not logically equivalent. This is Wednesday is not logically equivalent to this is not Wednesday. So double negation, if you think it's useful, you're wrong. It's not useful. It's just kind of a tidy up measure. In practice, when you get good at this, you don't really need to use it, because you sort of do it automatically. However, I'm going to use it now to illustrate a couple of points about that make the equivalence, the rules of equivalence. Hey, that was easy. I told you to stop and you stopped. If only that always works. Well, that's very good. If you start turning purple, I will allow you to cough. All right. The other thing about rules of equivalence, the first thing that I'm telling you is that they work in both directions. This is unlike with even the one premise equivalent inference forms. So for example, you can get, from P and Q, you can get P by simplification. But you can't then go back and get P and Q by simplification. It doesn't work like that. It only works in one direction. Whereas with the equivalence forms, because both sides of the equivalence symbol are equivalent to each other, then you can replace the one on the left with the one on the right, and vice versa, the one on the right with the one on the left. So if I did double negation again to this, I could get back to P. So in other words, if you ever apply an equivalence rule twice, you will always be back where you started. So that's the first point. They work in both directions. So in effect, you're getting two rules for the price of one. You're getting the rule that moves from the left to the right, and the rule that moves from the right to the left. The other key difference between, one thing to notice as well is there aren't any two-premise rules of equivalence. There are 7 two-premise inference forms, 7 syllogisms. There are exactly 0 two-premise equivalence forms, because you're just saying that one thing is equivalent to one other thing. So, in other words, you're only ever going to have one line reference when you're doing an equivalence form. That would be double negation. Okay, here's the other, and perhaps even more important difference between the two. That is, you can apply rules of equivalence to parts of lines. So exactly not like I said with inference forms. So for example, suppose we start with P and Q and then R. What will I get if I do double negation to it? Well, any of a number of things. I can apply double negation to the entire line and get this. That would be one thing. But I can also apply double negation just to the antecedent. And that's perfectly okay. That's fine too. I can apply double negation to just P. I can apply double negation to just Q. And I can apply double negation to just R. All of these are totally legit. And the reason why you can do this is because these two things are literally equivalent. That is, whenever this is true, this is true. Whenever this is false, this is false. So it's like taking a sentence, taking out a word and replacing it with one that means exactly the same. You haven't changed the meaning of the sentence, so you're allowed to do that. So here, if if P stands for bachelor and not P stood for unmarried man, then I could take out bachelor and slap in unmarried man, and the truth conditions of the long, think of this as like a sentence, the truth conditions of that haven't changed. So that's why it's okay. This gives you a lot more flexibility, but at the same time, when you're asked to identify rules of equivalence, it makes it a little trickier than inference forms. The only thing you shouldn't do is apply it more than once in one go. So if I were to say, something like this, that's actually two instances of double negation. I should do this one first and then this one. So if I said that came from double negation from line 1, that wouldn't be right because I've done it twice. But if I said this came from double negation to line 6, then that would be okay because then I've only added one set of double negations. Let's write that. Okay so far? Make sense? All right. That's the most obvious of them. Now perhaps the least obvious of them, and the weirdest, is the one that comes first. It's tautology. It's not one that you will use much. However, unlike double negation, you might say, oh yes, tautology is the one thing that I need here. That might happen. So, basically, it's saying that today is Wednesday is equivalent to today is Wednesday or today is Wednesday. Huh? And it's also equivalent to today is Wednesday and today is Wednesday. Yeah, this isn't going to come up in conversation much. However, you can do it. The only time it would come up is if you need it to solve a proof. And they are logically equivalent, however weird it seems, and we can prove that. How do we prove logical equivalence? What do we use? Everyone's coughing, sneezing. Truth tables, that's right. So, I guess so. How many truth values is it possible for P to have?
2.
2. True and false. When P is true, P or P will be true or true. What is true or true? True. When P is false, P or P will be false or false, which is false. Look, they're logically equivalent. Anytime P is true, P or P is true. Anytime P is false, P or P is false. Same with P and P. True and true is true. False and false is false. So they are logically equivalent. That's all you need for a rule of equivalence, even if it's a little wacky. Now, you might have noticed that suppose I start with P and P on one line, well I can get P by tautology on line 1. There's another rule that you've already learnt that would also give you the same result. What is that?
Simplification.
Simplification. Yes. However, what simplification won't allow you to do is to go the other way. Which tautology will. And also, simplification wouldn't allow you to do this. Whereas tautology would, because you can apply tautology just to this part of it. Whereas it, sure. You can apply tautology just to this part of it, whereas you couldn't do simplification just to that part of it. Okay? And of course, if you started with P, you could get P or P by tautology. You could also get it by, what other rule? What's that?
Addition.
Addition, that's right. And of course you could get P or anything with addition. But of course, you can't go from P or P to P by addition. And you can't do it in part of a line, which you can with tautology. So tautology is a lot more flexible. Alright, so that's tautology and double negation. A freaking obvious one and a slightly weird one. Now, for a while now, for the next few ones, we're out there, they're going to work on conjunction and disjunction and not on conditional. The first of these is called commutation. Now, for you math nerds, that should be familiar. And in fact, I've already talked about this. Which of the simple arithmetic functions, addition, subtraction, multiplication, and division, is commutative, or are commutative? Addition and multiplication. What does it mean to say that addition and multiplication are commutative?
Doesn't matter which way.
Yeah, it doesn't matter which way around you write it. In other words, 2 plus 3 equals 3 plus 2. Doesn't matter which way around you write it. Of course, that is not true of subtraction. 2 minus 3 does not equal 3 minus 2. So subtraction and division are not commutative. Well, of the truth functions, we've already seen that disjunction and conjunction are commutative. So what that means is that A or B, if you did commutation to it, it gives you what?
B or A.
B or A, that's right. Or A and B becomes B and A. Okay? So commutation just means changing the order. Now, suppose I have A or B and C. I can do commutation on either of those. I just can't do them both at once. So I could do commutation to get this, and I have to leave the rest of the line the same. So that would be a perfectly applicable commutation, or I could do this. So either of those things is perfectly okay. I can do commutation to this one and change the order like that, or I can do commutation to this one and change the order like that. It's like I'm treating the connective as a pivot. So here I treat this as a pivot and flip those around. Here I treat this as a pivot and flip those around. Okay, once again you can do it to just parts of lines. Make sense? Alright, think of one way to remember that this is what commutativity does. It works for me, I don't know if it'll work for you. What is commuting?
Traveling
Traveling specifically where?
back and forth to a place, like, for example, here.
Yeah, usually work. Yeah, so you commute to work. So commuting is going somewhere and coming back. In other words, you go in both directions. So think of it as going in both directions. If that helps you, fine. If it doesn't, I never said it. Alright, so that's commutativity. Again, something that we should be familiar with from pretty basic math. Also, something we should be familiar with from pretty basic math. Suppose I have 2 plus 3 plus 4. Now, suppose I'm a stickler and I say, I don't like seeing that, I want parentheses. Does it matter if I put them here? Does it make a difference where I put them?
Not even slightly.
Not even slightly, yes, because this equals 5 plus 4, which equals 9, whereas this equals 2 plus 7, which equals 9. So in other words, it doesn't matter, when I have two pluses, it doesn't matter where I put the parentheses. So in other words, something where the parentheses are here is equivalent to something where the parentheses are here. Well, the same applies for and or. So A and B and C is logically equivalent to, you can move the parentheses to A and B and C. And this rule is called association, because you are changing which two are associated together. Here B and C are associated together, and you can switch it so that A and B are associated together. And it doesn't matter, provided this works when you have two ands or if you have two ors. But it doesn't work when you have a mixture. So if one of them is an and the other is an or, like here, you can't move the parentheses. You can only move the parentheses when they're both the same. When one of them is, when they're both ands or they're both ors. So A or B or C. If you did association to it, it would be A or B or C. I suck. Make sense? So far so good? Alright, now you might wonder to yourself, how would this ever come up in a proof? I know you're wondering that. Well, I am going to show you how it might come up in a proof. So bear with me. Here is something for you to prove. And you will need to use both commutation and association plus one of the syllogisms. So there is the argument you have to prove. First premise, P or Q or R. Second premise, not Q. Conclusion, P or R. Prove it. Actually, I've just realized that I've overcomplicated things a little. So I'm going to, yeah, you'd have to use one extra step if I didn't do this. So I apologize for what I'm about to do. I'm going to do that. Sorry. So it's P or Q or R. There. You could do it the other way, you just need one more step and it'd be a bit repetitive. You got it? Who else has got it? Good. What is the first rule that you use?
Association.
Association. That wouldn't be the first one that I use. What's that? Commutation. I think. Now, I'm sure you can do it by doing association first, but you might need an extra step. Whereas commutation is probably simpler. All right, so let's say you do commutation. What premise would it have to be on? Premise 1, because it can't be on premise 2 because there's nothing to change the order of. So it has to be on premise 1. Now there are two possibilities because there are two ors. You can either switch the order of Q and P or you can switch the order of R to the front of here. Which is it? Switching the order of Q and P. So that will give me what? If I switch the order, if I do commutation to this, let's pick someone to pick on. Yeah, cat. What would commutation to this give me? Yes, and then the rest of the line would be unchanged. So it would look like that. That's com1. Now, why did they do that? Well, because of what I'm about to do next. What am I about to do next?
Use association.
use association. Now, obviously it's going to be on the line that I just produced. So what would association on line 3 give me? Show about.
You come back together.
No, because association just means moving parentheses. So what's it going to give me?
Give you P,
No?
Q, or parentheses, P or R.
That's right. Now, somebody who has not yet solved it, this is where you solve it. We are one step away from the conclusion. So the conclusion will be on the next line. The conclusion is P or R. How did I get that? Somebody who didn't solve it yet. Did you solve it already? Well then, shush. Somebody who had not yet solved it. How did I get that? What was that? What was that little mouse back there? If disjunctive syllogism, what 2 lines? No. Yeah, 4 and 2. I'm going to write them in that order because I write the disjunction first. So it will be ds 4, 2. That's right. Because here you have a disjunction, you have Q or this, and then you have not Q, so it must be this, which is P or R, which is what we wanted. So, basically, when you get used to this, you'll see something like this and you'll think, well, there's the P and the R, and I can get rid of the Q with this not Q by doing disjunctive syllogism. I just have to get that Q out in the open somehow. It's buried in there. I have to find a way to get it on the outside so I can sort of knock it off with this not Q. And the way to do that is to just flip the order of that and then change the parentheses, and there it is. It's exposed. It can be picked off. That's how commutation and association might be useful in a proof. All right? Okay. Distribution, another one that you should be familiar with from fairly simple math. To wit, suppose I have 2a plus b. What is that equal to?
2a's plus 2b's.
2a plus 2b. Right? Everybody knows that. What is that? Is that algebra? We just did. Well, probably somebody at some point in my schooling used that word, but I just always thought of it as all math kind of blurred together. Now, this is called distribution. What isn't being sort of included there, because you're allowed to omit them for shorthand in math, is the multiplication symbols. Where are there implied multiplication symbols? Here, here, and here, right? So 2 times a plus b equals 2 times a plus 2 times b, right? That's exactly equivalent to what goes on with the truth functions, conjunction and disjunction. So if I had p or q and r, what would that be logically equivalent to by analogy? P or Q and P or R. That's exactly right. That's distribution. Or alternatively, it works if you have P and Q or R. That's logically equivalent to what? P and Q or P and R. Now one of these is going to be more useful, and it's this one. It's going to be more useful because you start with a disjunction and it becomes a conjunction with, and what can you always do with conjunctions? Simplify them. So this one will probably be more useful to you. Although maybe something like this will come up. Also, it's very important to remember, what is true about rules of equivalence? They work both ways. So you could start with something like this and end up with something like this. Now that seems an odd thing to call distribution. It looks more like condensation, because instead of 2 p's, you end up with 1 p. But it's called distribution either way. Okay? So again, I think that one's easier if you just think of it as equivalent to the distribution that you're familiar with in math. Alright? Now, I could make you prove that these are logically equivalent using truth tables. How many lines would your truth tables need to prove that this is logically equivalent to this? How many rows?
8.
What's that?
8.
8. Because there's 3 different letters. 2 times 2 times 2 is 8. I'm not going to, but you could. If you were very picky and you're very suspicious, you should test to see if they're in fact logically equivalent. Spoiler alert, they are. Okay, that's distribution. Oh, here comes another one. We've talked about this a lot, and every time we talked about it I said, that's De Morgan's law, but you don't have to know that yet. Well, no longer will I say that, because you have to know it now. You have to know what De Morgan's law is. And the first time it came up was when we were talking about disjunctions. And I said there was one non-standard way of expressing a disjunction, and it came up with the example of, I can't both do the dinner and take out the trash. So I can't both do the dinner and take out the trash became logically equivalent to, I can't take out the I can't do the dinner, or I can't take out the trash. So notice what this is saying. Well, first of all, what's changed? You can think of this a little bit, well, I always say this and then people call it distribution by mistake. So don't do that. But you can think of this as like distributing the tilde. But it's not distribution, it's De Morgan's law. Give the man his credit. So you distribute the tilde, get rid of the parentheses, and one more change. What is the one more change?
Change the and to an or.
The and to an or vice versa. So if you have not D or T, it's logically equivalent to not D. I'm waiting for you to fill this in. And not T. Which makes sense if you think about it. This is saying I'm not going to do both. Which leaves open the possibility that you'll do one, you're just not going to do both. So either you're not going to do one or you're not going to do that or the other. Whereas this one says I'm not going to do either of them. That means I'm not going to do that one and I'm not going to do that one. Right? I'm not going to do either of these. Okay? This one says I'm not going to do them both together. This one says I'm not going to do either of them. Alright? And again, remember, you can do this on parts of lines. So if you have something like this, not D or T, then E, that can become not D and not T, then E, by De Morgan's law. And of course it works in both directions. So you can either distribute the tilde or you can take the tilde outside and add parentheses. So basically you're getting 4 rules for the price of 1. Bargain. Okay? We're kind of blitzing through these, but they're on your homework. Contraposition, hey, a familiar one. All right, we've done the rules that apply just to conjunction and or disjunction, and now finally, conditional gets a say. Well, you can't do commutation to conditional. You can do commutation to conjunction, so A and B is equivalent to B and A. But you can't do commutation to conditional, because if P then Q is not equivalent to if Q then P. If you're a whale then you're a mammal is not equivalent to if you're a mammal then you're a whale. But if you're a whale then you're a mammal is equivalent to
If you're not a mammal, then you're not a whale.
right. And that's contraposition, which we've already learned. Remember contraposition? Of course you do. Good times. So that's contraposition. You just have to remember that if you're going to change the order of a conditional, you also have to negate both the antecedent and the consequent. Now, I'm kind of glossing over, I'm actually doing something which I don't normally do, which is I'm using letters. I probably should use shapes. So I should say something like this. You start with that and you end up with this by contraposition. But also, what if I start with if P then not Q? What does contraposition give me? If Q then not P, that's right. Now if you're a stickler, you can just add a tilde on both sides. So you could say this, so you could start with this and it would give you not Q then not P. So you don't want to think about it, you just want to always add a tilde. If you do it that, then you can get rid of these two by what rule? Double negation, which is why I called it the tidy up rule. But you know, you don't have to do that extra step unless you want to. You can just go straight from this one to this one if you like. I don't care. All right? And of course, it works on parts of lines. So you have, suppose you have if P then Q then R. You can do contraposition to this one. Get if not Q then not P then R. Or you can do it to that one. So you have if not R, then if not, I'm sorry, if not P, then Q. So you switch the order around that one, or you switch the order around that one. Either one of those is okay. Yeah? Everybody following? Does anyone want me to do that again? Or you? Okay, so suppose I'm just repeating what I said before. You can do any rule of equivalence in which contraposition is 1 can be done on a part of a line. So suppose this is line 1 and I want to do contraposition to it. Well, there's two different conditionals I could do it to. If I do it to this one, then the rest of the line is going to stay the same, right? So I'm not going to change this one. So I leave that the same. But if I do contraposition to this, I'm going to switch the position of Q and P and negate them. So that's what I'd end up with. Alternatively, I could do it to this one, in which case this is going to stay the same. It's just going to move over here and it's going to be negated. And then R is going to go up the front and that's going to be negated. See what I'm saying? So either I'm doing contraposition to this, in which case we end up with this one, or I'm doing contraposition to this one, in which case I switch the order here and negate R and this whole thing. Yeah? Either one of those is okay. It just depends which you need for your proof. Okay. Now we come to implication. We've already done implication. Only I didn't call it implication. I called it the Aerosmith Rule. Why did I call it the Aerosmith Rule? Because I'm insane. No, it's because of an example I used. What was that? What's that?
You don't love Aerosmith and you won't.
Either you don't love Aerosmith or you want his tickets is equivalent to if you do love Aerosmith, then you want these tickets. Yeah. So basically, this is implication is when you want to change a conditional into a disjunction, or vice versa, or you want to turn a conditional into a conjunction, or vice versa. Although it's not strictly a conjunction. However, so let's say you start out with if P then Q. What is if P then Q equivalent to? Well, let's use our truth table. True, false, true, false, true, true, false, false. What's the truth table for conditional? True, false, true, true. Now, we know that that's going to be equivalent to some disjunction. because there are 3 trues and a false. We just want to set it up so that it is a disjunction that is false when P is true and Q is false. What disjunction? Well, first of all, when is a disjunction false? When they're both false. So what disjunction is both of them going to be false when P is true and Q is false? Obviously one of them is going to be Q, because that's already false. But the other one's going to be not P. Yes, because we want it to be false when P is true. What is false when P is true? Not P. So then we see that this is going to have the same truth table, which is not that. What are you doing? I'm on a roll today. I always do this when the camera's rolling. Okay, now, it turns out, well, let's put it this way. Will there be a conjunction that is equivalent to these? Yes or no?
Yes.
No. Why not? Well, what do we know about the truth table for conjunction?
It's only true once.
It's only true once. These are true 3 times. Okay, but what kind of thing, if a conjunction is only true once and false 3 times, what kind of thing will be true 3 times and false once?
Negation.
The negation of a conjunction. So in other words, we're going to negate a conjunction. What conjunction? The conjunction that is going to be true on this line. Because then when we negate it, so it's going to be false, true, false, false, and then when we negate it, it's going to be true, false, true, true, which will make it equivalent. What conjunction is false when P is true and Q is false? I'm sorry. What conjunction is true when P is true and Q is false?
P and not Q.
P and not Q. Because P we keep the same because it's already true. And then we want something that is true when Q is false. Well, that's not Q. So that's going to be false, true, false, false. And then when we negate it, it's going to be the opposite. True, false, true, true. So implication will take you between these two or between these two. Implication always involves a conditional. Either you start with a conditional and change it into one of these two, or you start with one of these two and end with a conditional. But obviously these two are also going to be equivalent because they're both equivalent to the same thing, so they'll be equivalent to each other. However, you don't use implication to convert this one into this one or vice versa. What do you use? De Morgan's law. So if you're using implication, it's always going to involve a conditional. If you want to convert between an or and the negation of an and, you're using De Morgan's law. Now, implication, besides being my favorite rule of equivalence, involves a fair amount of different permutations. And it's probably the most commonly used. Well, certainly it's up there. It's one of the, I'd say it's one of the top 3 commonly used rules of equivalence. So you're going to have to get the hang of it. So, here are the rules. When converting between conditional and disjunction, follow these 2 rules, and incidentally write down these 2 rules. First, you replace one connective with the other. So if you're starting with a conditional, you replace it with the or. If you're starting with the or, you replace it with the conditional. So these rules work whichever direction you're moving. Doesn't matter if you're starting with the disjunction or the conditional. So, replace one connective with the other. Second rule, negate basically the one on the left. So if you're ending up with a disjunction, you negate the disjunction on the left. If you're ending up with a conditional, you negate the antecedent. Let's try. So, suppose we start with if P, then Q. Apply rule 1. we replace the conditional with the or. Apply rule 2, we negate the one on the left. Not P or Q. And that's the right answer. Now, let's apply it again and see if we end up with the original. So, first, replace one connective with the other. Now we're starting with an or, we replace it with a conditional. Negate the one on the left. Well, I can either double negate it, or I can just say, well, that'll cancel that out. And we're back where we started. Okay? So, this helps when you're getting odd things like this. Suppose I started with P or not Q. Just apply the rules. What will that be equivalent to?
P then not Q.
What's that?
Not P then not Q.
Yes. So we replace this with the then, and then we negate the one on the left, and you have if not P, then not Q.
What's the word, the last word, number 2?
This one? Antecedent. Remember, that's the first one in a conditional. It's basically, rule number 2 is just negate the one on the left. Whether it's a disjunct because you started with a conditional, or it's a conditional because you started with a disjunct. All right, so that's when you're converting between a conditional and a disjunction. What about when you're converting between a conditional and the negation of a conjunction? You have 3 rules. The first one is the same. You replace one connection with the other. This time, though, you negate the one on the right. You negate the conjunct on the right or the consequent. And then finally, the extra rule is you negate the whole thing. So, again, if we start with if P then Q, first of all, we replace the conditional with the and. You negate the one on the right. And then you negate the whole thing. And it's not P and not Q, as we wanted. Oh, one more thing to point out. Why, if you think about it, is it kind of obvious that this is equivalent to this? Yes.
Since Q is a necessary condition for P, you can't have P and not Q.
That's right. That's true. Which is another way of saying, if you think of the truth table for conditional, what is the only time that it's false? When P is true and Q is false. So the conditional is not that. It is not. So a conditional is true when it is not the case that P is true and Q is false. That's when a conditional is true. So, if you're a whale, then you're a mammal. Either you're not a whale or you're a mammal. It is not the case that you can both be a whale and not be a mammal. They're all equivalent. Okay. Sure. Not good enough? So, as I said, implication comes in many permutations. Make sure you get comfortable with implication. All right, we're nearly there. We just have 2 rules left. Biconditional. Biconditional is the only rule that works on the biconditional. So if you have a biconditional in your proof, you'll need this rule. And I think I already asked you to prove this once. Let's see. So we have what are the words that this stands for? If and only if. So P if Q is actually this. And P only if Q is actually this. So if and only if, look looks like that. So this is equivalent to this. Perhaps an easier way of thinking about it is there is another symbol that is sometimes used instead of that for if and only if. I told you what it was. Can you remember? It's a... What's that?
I double L.
No, that's just an abbreviation of if and only if.
Double-ended
It's an arrow going in both directions, yes. So if you think of this as like that, well, you got the arrow going from P to Q, and you've got the arrow going from Q to P. That's what they're equivalent to. Let's see. Yes. So here is a trying to be lazy. Okay, so we can prove it using a truth table. We know that there's only one time that if P then Q is false, and that's on this line. What line is if Q then P false on? Not the second, that's when if P then Q is false. The third, because that's when the antecedent Q is true and the consequent P is false. So it's going to be like that. Now, the rest of the time it's going to be true and true, which is true. It's going to be false and true, which is false. It's going to be true and false, which is false. And then it's going to be true and true, which is true. Hey, that's the truth table for biconditional. All right, now there is one other thing that biconditional will get you. But I have to say, I have never used it in all my years of teaching this class. So using biconditional, you can either convert this into this or this into this. Occasionally you will need to convert something like this into this. It will come up. Or you can convert this into this or vice versa. What's this one? Well, again, this is a bit like a description of the truth table for biconditional. When is a biconditional true? When P and Q are true, or when P and Q are false. So that's going to be true or false, false or false, false or false, false or true. So because it's or, this one and this one are going to be true, and it's going to have the same truth table. But as I said, if you allow yourself to forget one thing, I would say you can allow yourself to forget this one. Incidentally, though, you're going to have to learn all 19 rules. They're not going to be given to you on the final. You're going to have to learn them. So the sooner you learn them, the better you'll be. And in fact, the sooner you learn them, the easier the proofs will be. Because if you know the rules, if the rules are there in your brain, you can just look at something and a strategy will sort of form itself immediately. You say, oh, I can do implication there, and then I can do disjunctive syllogism, and it'll come much quicker. It's like learning vocabulary in a language. If you've learned the vocabulary, translation is a breeze. If you have to rely on looking it up in the book, translation is torture. So learn the rules. If you absolutely cannot learn the rules, I give you one other option. You can tattoo them on your body. I will allow that. But they have to be permanent tattoos. Nobody has yet taken me up on that. But I think that would be a pretty freaking awesome tattoo, because nerdy tattoos are cool, right? Yeah.
You say permanent, like as in permanent marker?
No, that is not a tattoo. There's a difference between writing and a tattoo. It has to involve pain. Okay, no pain, no gain. Last rule, exportation. It looks like this. If P and Q then R is equivalent to if P, then if Q then R. You could prove it. How many rows would your truth table need if you were to prove that these are equivalent? 8. In fact, I think you already have, because I believe when we were doing truth tables for equivalent, I had you test these for equivalence, knowing, of course, that they would be equivalent because I know exploitation. Let me think of it this way. So if I shoot you and we're far from a hospital, then you will die. Is equivalent to, if I shoot you, then if we're far from a hospital, then you'll die. Cheery thought. Good thing I'm not going to shoot you. Probably if I shot you, I'd miss. So. There you go. That's equivalent. Exportation comes up sometimes. Let's see how good we are at recognizing them before you're actually required to do it for the homework, which some of you have already done. I've lost my place. Here we go. Turn to page 398. 398. Go to page 400, go back 2 pages. Go there. Okay, I'm going to pick on you again, Charbel, so you're ready this time. What is number 1 an instance of? You shouldn't have to look this one up.
It's the double negation.
It is double negation. Good. Moving backwards. Nick, what is that? That's not a rule. Well, what's changed? What's changed between the top line and the bottom line?
Parentheses.
The parentheses are moved. In other words, D and E were grouped together, and now E and F are grouped together.
That would be
What's another name for a group?
district.
No, that's not another name for a group. An association, as in the National Basketball Group. Yes, so that is a sock. Association. Number 3. So, is it implication? Is it implication? No, it is not implication. Why isn't it implication? What must implication always involve? A conditional. Now this does have a conditional, but that's not what changes. What changes is these. So it's not implication, it is, remember his name?
Distribution.
Not distribution. See, I knew I shouldn't have said that. Distributing the tilde. It's De Morgan's law. Yes, De Morgan's law. That is, there's no intuitive connection between what it is and that name. You just have to remember the name. Because he's got, his name must go down in history. All right, number 4, Ryan.
Implication.
That's implication, my favorite. All right, number 5. Destin. What's changed between the sign hasn't changed. This one's a conditional and this one's a conditional. So what has changed? The order, and we've added these. What's that called? No, something else beginning with CO. Yes, contraposition. That is contraposition. Good. Number 6. Eric. You guys are slow. Come on, faster, faster, faster.
Distribution.
Number 6. You're telling me number 6 is distribution. Stop telling me that, because it's not true.
Okay, well then it's not distribution.
Yes, that's one thing we've eliminated. Now we're down to 9 possibilities. What's changed?
Oh, it's
Yes, yes?
association.
No. Association doesn't change the order. This one's changed the order. What changes the order? Commutation. Thank you. Number 7. Samantha. What's changed? It's now repeating itself. So you've got double. What is it that allows you to double something? It's pretty weird.
It is what it is.
This word is sometimes used when somebody repeats themselves. You say that's a, because that's what you're doing, you're repeating yourself. What's the word?
Tautology.
Tautology. Anyone heard that word used that way? No? Kids these days. All right, number 8.
Number
Jake.
8. Adults.
Relative. What's changed?
The negative. Oh, that is.
Yeah, you can peek, you're allowed to look. You don't have to memorize them all just yet. It's my favorite.
Is that communication?
No, that's not my favorite. I don't think that's a rule. Communication.
No,
No, not that one. That's when you change the order. What is it?
Oh,
Implication.
Implication. Yes, that's the one.
That's the one I was.
All right, yes, that's the one you were thinking of when you said all those other ones. All right, so that's implication because notice this has not had implication done to it. Only this part of the line has had implication done to it. But you can do that with rules of equivalence. Number 9. Dana.
Distribution.
Is it distribution? Yes, it is. Well spotted, because actually we've done it kind of in reverse. In fact, I diagrammed this one out earlier. So if you think of triangle to stand for K and L, it's triangle or, square stands for if M then N, and O. And the bottom line looks like this, triangle or square and triangle or O. And when you write it out like that, I hope it's clearer that it's distribution. But you saw it anyway, stop cracking your knuckles. All right, so you lost all the goodwill that you gained from that one, like that one act. Okay, this one, number 10, Brandy.
Biconditional.
Biconditional, yes, that's always nice when you see that, you think, yes. All right, number 11, Hunter.
I had,
If you had it, you would already know it, but you seem to be looking for it.
I changed it.
Oh, okay. Anyone?
Exportation.
Exportation, yes, we have this and G, then this whole thing becomes if this, then, if G, then this whole thing. Number 12.
Association?
Number 12. You said association? No, it is not association.
Biconditional?
No, it's not biconditional. That hasn't changed. Yes, it's included, but notice it's got longer. With association, it wouldn't get longer. You just move the parentheses. Why has it gotten longer?
Just because this is an equivalent tautology, got it.
Yes, what's happened is this is the only part of the whole line that the rule has been applied to. Everything else is a red herring. So basically it's L has become L or L, which is tautology. Isn't that one a nasty one? Don't.
13.
Yes, unlucky for some.
Case of communication.
Commutation, yes. In this case, the A and the C have just switched places. Commutation. Everything else stays the same. Ethan, number 14.
I'm not sure about that one. I don't like the look of it.
Well, if you start on the bottom and end up with the top, you might like it better.
It's distribution.
It is distribution, yes, I think so. Because the E, you've got 2 E and Fs here, and you've only got 1 here. Number 15.
The Morgan's law.
Is it De Morgan's law? Let's see. Yes, we got a negation of an and becomes a negation of one or a negation of the other. Yes, that's De Morgan's law. All right. Now, let's put these. There's a point to learning these rules. other than just causing you pain, which, you know, has some value in itself. And that is so that you can use them in proofs. Let's look at page 388. Right now, before we forget, if you're renting your textbook, you probably won't want to do this, but if, as you should have done, you've invested in this textbook and you will treasure it for always, you can scribble out angrily number 2. Because this one is invalid. It is impossible to prove. So it's kind of a nasty trick to have it in there. Now, it must be a misprint of some kind, but actually there's not much that you could fix really to make that a valid argument. So if you tried to prove that one, either you would do it wrong or you would go on to infinity, neither of which would be a good thing to happen. But the rest of them are okay. The rest of them work. Let's see. Let's see if we can prove the first one. So, this one is a good instance of where we would apply what I call the bottom-up method. Now, in case you'd forgotten, the bottom-up method is when you just kind of ignore the conclusion and just mess around and see what you can do. And when I say mess around and see what you can do, I should qualify that now, because you've learned a whole lot of rules of equivalence. And now you've got rules of equivalence, there's a bazillion things you could do, most of which would be totally pointless. So when I say mess around and see what you can do, I mean using the 7 syllogisms. Because it's only by using the syllogisms, 7 out of the 9 inference forms, that you can combine 2 lines. Right? You can combine. It's only by using a syllogism that you're combining the information in 2 premises. All the rest of the time, you're just fiddling around with 1 premise. Whereas of course, the premises will only guarantee the conclusion by working together. So, long story short, you want to see if you can do some of the syllogisms. So with that in mind, let's look at this one. Here's how you'd write it out to begin with. Premise, 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 / conclusion. But we're going to ignore the conclusion. We're going to forget about the conclusion. We're just going to look at the premises and say, see if there's a syllogism that leaps out at us. Is there? No, because implication, remember, will allow you to convert from the negation of a conjunction as well as from a disjunction.
Oh, I
Told you implication would come in handy. I told you. It's my favorite for a reason.
These are all on logic.
That one. Do any 2 of those 3 premises go together to form an inference form? 1 and 3. What is that inference form called? Modus ponens. Yes. So modus ponens 1, 3 will give us what?
B.
If A, then B. A, conclusion B. All right. We're still ignoring the conclusion. Now we say, oh, actually, I'm going to do one thing that, because I figure I might as well use a rule of equivalence, I'm going to do this. You don't have to, and as I said, double negation is never really much used. But I'm just going to do it so that it becomes kind of obvious what we're going to do with that. So now we've got not B. Is there something else that leaps out at us? Are there 2 lines that will go together in another syllogism? 2 and 4. So we have not B or C. Well, it's not B, so it is C. Now would be a good time. Oh, and what was that, by the way? What did we just do? Disjunctive syllogism, lines 2, 5. Now would be a good time to look at the conclusion. Why?
We're there.
Because we're done. We proved it without even trying to. We just messed around and got a triple-double. No, we messed around and proved that argument. All right. Skip over number 2. And here is my challenge to you. You may go as soon as you have proved number 3. If you do not prove number 3, you have to stay here forever. We'll call the ACLU or something. All right, now this one is actually probably the better way to think of this is the top-down method. So we look at the conclusion and we say, where must this conclusion have come from? Well, where does H show up? First premise. Where does K show up? Second premise. So we're going to have to combine those 2 premises. So we're going to have to combine 2 premises and end up with a conditional. What inference form does that sound like? What inference form, what kind of syllogism ends up with a hypothetical? A hypothetical syllogism, yes. Can you do a hypothetical syllogism as it stands? No, because this is not a conditional. If only there was a rule that converted something that looks like this into a hypothetical. If only. A rule of equivalence, so to speak. Anyone got it yet? All right, let's see your work. Yeah, just finish it, and then you're done. Yep. Who else had it? You did, Josh. Yep, you can go. Rest of you are getting worried. Well, let me see.
Sort of allude to